Hello everyone, this is Dr. Lennon, and today I'd like to talk about the derivative function. We'll start by looking at the idea, and the idea just essentially comes from the derivative at a point, taking the average rate of change. So let's recall the average rate of change. What we're doing there is we have some graph. So the picture, you have some curve, and you're essentially finding the slope between 2 points on that curve, or at least of the line that connects those 2 points. So you've got some curve, maybe a shape like this. You've got 2 points, A and B, and the average rate of change is the slope of the dotted line between them. So the average rate of change was given by essentially the formula f of b minus f of a divided by b minus a. So what we want to do for the derivative, so the idea of the derivative is to find the slope of a tangent line to a curve at a single point. So it really comes out of the average rate of change formula. What we do is we just take the previous formula and apply a limit. So find the slope of a tangent line at a single point. So what that entails is we have, some picture again, and you have some point, maybe we call it A, and what we'd want to do is we'd want to find the tangent line, so the line that just touches the curve and is perfectly tangent. We'd want to know what is the slope of that dotted line. So the derivative at that point, so the slope of the dotted line this is known as the derivative of f at a, and it's denoted by f prime of a. So the derivative of f of x at a. So how do we incorporate that as a limit? Well, really what's going on is we want to think about the average rate of change idea, but just shrinking the interval. So if you have A and you wanted to look at the same kind of picture, what you would do is you would look at a series of points that get closer and closer to A. So if A is right here, we might start way over here and look at that line, and then get closer and look at that line, and then get closer and look at that line. So there's some small distance between the points you're looking at. We can call that h, which would make this point up here a plus h. So if h represents the distance between A and the nearby point we're looking at, we can take the limit as h goes to 0, and we're going to find exactly the derivative. So what would that look like? Well, your 2 points are A and A plus H, and the x and the y values would be f of a and f of a plus h. So your if you kind of did the limit as h goes to 0, you'd be looking at f of a plus h minus f of a divided by a plus h minus a. So in the denominators, both of those a's will cancel, and we just end up with the limit as h goes to 0 of f of a plus h minus f of a over h. And that's how we define the derivative at a point. So if you define it at a single point A, it's differentiable at that point. If you have a nice smooth curve with no sharp corners in it, then you can talk about the derivative function. So there will actually be a formula that you can plug these things into that will give you the derivative at every single point. And that's what the derivative function is. So let's write down that definition. It's essentially this definition we've just written here, but we're replacing a with x. So definition, the derivative function f of x is defined by f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. So now we can find derivative formulas for lots of the functions that we have been looking at. And a lot of those will incorporate the algebraic trickery used in solving these limits. So let's go ahead and compute the derivative of a few functions using those limit techniques that we looked at in a previous lecture. So we're going to do this at first using these definitions to derive them, and then in the future we'll have shortcut ways to extend these rules to the broader class of function in which they live. So let's compute the derivative of each function. Using the definition. So the first one we'll look at is just the parabola with vertex 0, 0, f of x equals x squared. So pretty straightforward. We're just going to apply the limit. So f prime of x will be the limit as h goes to 0. And remember, what we need to do is we need to plug x plus h into the f of x formula. So the first thing on top is going to be x plus h quantity squared. That's f of x plus h. Then minus f of x, which is just the formula x squared, and we're dividing by h. So we can't plug in h equals 0 now because there's the that would cause division by 0. So what we need to do is expand and collect and hopefully factor. So this is the limit as h goes to 0. Of x squared plus 2xh plus h squared minus x squared over h. And remember, you want to write down a limit so long as there are still h's in the problem. So both of these x squareds are going to cancel out, and we end up with a limit as h goes to 0. The two remaining terms in the top both have an h, so we can factor that h out, and we get 2x plus h over h. Now we can cross off that h, and we're just left with the limit as h goes to 0 of 2x plus h. So we can plug in 0 for h, and we get 2x as the derivative formula for f of x equals x squared. So pretty straightforward. That's one of the easier examples where we just factor. Let's do a similar one just for practice, but maybe we'll have more than a single term this time. So for part B, let's look at g of x equals 5x squared minus x. So what do we end up with here? Well, again, let's just start by the definition. G prime of x, it's going to be a limit as h approaches 0. And we're doing g of x plus h first. So anywhere you see an x in the g of x formula, you want to replace it by x plus h in parentheses. So we're going to have 5 and then x plus h squared and then minus x plus h. Okay, so that's g of x plus h. Now we want to subtract regular g of x. So we're going to take the g of x formula, put it in parentheses, and take it away. So we end up with minus 5x squared minus x, and then we divide by h. So what can we do now? Well, now we can basically just go ahead and start expanding everything and see what cancels. So this will be the limit as h approaches 0 of 5 FOIL out x plus h, which is x squared plus 2xh plus h squared. And then we subtract x and subtract h. Then distribute the negative to the remaining two terms in the top of the numerator there. So minus 5x squared plus x over h. So we see two things canceling here, the minus x and the plus x cross out. So we have limit as h goes to 0. Now we want to distribute that 5. So we have 5x squared plus 10xh plus 5h squared minus h minus 5x squared. So now what's going on? And on top, the minus 5x squared terms are being crossed off. And this is, again, all over h. So there's 3 terms remaining in the numerator of this limit, and they all contain a factor of h. So what we're going to do is we're going to factor out that h. So we end up with the limit as h goes to 0 of h times 10x plus 5h minus 1 divided by h. So we just now replace the final h by 0 because we've eliminated that problematic h in the denominator. So we end up with just 10x minus 1 as our derivative. So those didn't require any of the excessive tricks. Essentially, you're just plugging things in, expanding, canceling, and then factoring to cancel that h in the denominator. Let's look at a couple more where we incorporate some of the other tricks that we've seen. So C, excuse me, let's try to find the derivative of h of x equals 7 times the square root of x. So again, h prime of x is going to be 7, sorry, we're doing the derivative, so we need to start with a limit. So we have the limit as h approaches 0 of 7 square root x plus h minus 7 square root x divided by h. And now think back to limits. Remember, one of the tricks whenever we see square roots, we want to think about multiplying by the conjugate. So that's exactly what we do right now. We multiply by the conjugate of the numerator. So that entails multiplying by 7 square root x plus h plus 7 square root x over 7 square root x plus h plus 7 square root x. And this is going to be the limit as h approaches 0 of, again, on top, basically that's all we're doing is doing a squared minus b squared. So we're going to get 7 times 7, 49 times the square root of x plus h squared, which cancels the square root. So 49 times x plus h minus 49 times x. And on bottom, we're just going to leave that alone, writing it as h times 7 square root x plus h plus 7 square root x. So again, if you do 7 square root x plus h squared, if you're curious about the top, it's because, right, 7 times the square root of x plus h squared minus 7 square root x squared is equal to 7x plus h. 49, sorry. Wrote it wrong when I tried to include more steps. All right, so 49 minus 49x. So that's why. So on top, what's going to happen? Well, we'll have 49x plus 49h minus 49x. So the numerator will only have 49h left. So that will allow us to cancel the h in the denominator. So this h cancels with this h. And what happens? Well, this is 49 over 7 square root x plus 0, which is x, plus 7 square root x, which is 49 over 14 square root x. Both of those have a common factor of 7, so this will reduce to 7 over 2 square root x, and that is the derivative of 7 square root x. So let's continue with a fraction. So that's the last trick that we saw from limits, finding a common denominator. So if we have f of x equals 8 over x, we start the same way as always. F prime of x is the limit as h approaches 0 of 8 over x plus h minus 8 over x, with everybody being divided by h. So we need to get a common denominator in the numerator, so we can do that by writing the limit as h goes to 0 of 8 over x plus h times x over x minus 8 over x times x plus h over x plus h. And again, everyone is still being divided by this h. So this is going to be the limit as h approaches 0 of 8x minus 8 times x plus h over the common denominator of x over x plus h, and then we're still dividing everything by h. So what's going to happen on top? Well, we're going to distribute the minus 8x, or the minus 8 to the x and to the h. So we'll have 8x minus 8x. Those will cancel, and we'll just have a minus 8h on the very top. So we have the limit as h approaches 0 of minus 8h over x times x plus h over this h. And now remember, the trick is to think of the h in the numerator. So we can think of this as one big fraction, and then the other one is a big fraction divided by 1. So really it's the same thing as the limit as h goes to 0. Remember, when you divide by a fraction, that's the same thing as multiplying by the reciprocal. So really what we are doing is we are multiplying by 1 over h. So the h's in fact cancel again, and we can plug in 0 for h. So we'll just have minus 8 times 1 on top, which is minus 8, and then we'll have x times x plus 0. So that's just x squared. So we have minus 8 over x squared, and that is the derivative for part D of this example. Okay, so we've done those examples using the tricks that we saw from applying the limits last time. Now let's look at some shortcut rules for at least ones that will allow us to multiply polynomials. So we're not going to prove these, but we will use them quite frequently. So you might have noticed a pattern already looking at some of the power functions and polynomials, but here are the shortcut rules. So basically the first one is the power rule. So that says if you are taking the derivative of anything into the form of like x to the n, the derivative of that is n times x to the n minus 1. So what you do is you bring the exponent down, multiply it in front, and then you subtract 1 from the exponent. Another rule, if you're multiplying a constant by a function of x, that doesn't really affect your result. So you can bring constants out when taking derivatives. So the constant out rule is as follows. If you have a constant times some function of x, and you're trying to take the derivative, well, really what you can do is just take the derivative of the function f of x and then multiply back by that c when you're done. So you can kind of pull the constant out of the derivative and just focus on taking the derivative of the function of x itself. And the third thing is the sum rule. So if you have two functions added together, f of x plus g of x, and you're trying to take the derivative of that entire function, you can just go part by part and then add them back together. So this is f prime of x plus g prime of x. And that's all. What that means is if we're looking at a polynomial, say something like 12x cubed minus 7x squared plus 10x minus 3, you can look at each of the four terms separately and just differentiate those. So rules 2 and 3 allow us to do that. So two special cases that I want to mention. So two special cases of rule number 1. So what are those? Well, if you're taking the derivative of some constant, sorry, I put the prime in the wrong spot. So when taking the derivative of a constant, that is just 0. And that makes sense. If you think about y equals any constant like y equals 5, its graph is just a horizontal line. Horizontal lines have slope 0. So the derivative of any constant function is just 0. Similarly, if you would look at, say, just some constant times x, k times x, where x is a constant, this is just going to have derivative k. So what that would correspond to is if you looked at some line through the origin, y equals kx, the tangent line is just the slope there, and the slope of this function is just going to be k. So the derivative of kx is k. Up here I'll write down y equals c. So a flat line or a horizontal line will have slope 0. So let's just look at 4 quick examples where we want to differentiate using these rules, and you should have the hang of it. And there's always more to practice on the homework if you want to try a little extra. So let's differentiate. So differentiate just means find the derivative. So let's say we have 8x cubed. Again, we can essentially ignore the 8 and then just look at the x cubed. So what would you do with x cubed? Well, you would bring down the 3, and then you would do 3 minus 1 in the exponent. So the result would be 24x squared. So that's just by, this is by rule number 1, which we call the power rule. And technically by rule number 1 and number 2, because we could think of pulling that constant of 8 out. For B, let's look at a polynomial, something like 7x squared minus 5x plus the square root of 2. We want to find the derivative of that. Again, we're just going part by part. So if you want to think of this, we're really just finding the derivative of 7x squared minus the derivative of 5x plus the derivative of the square root of 2. So this would be by rule number 3. And by rules number 1 and 2, the derivative of x squared would be 2 times x. So this would be 7 times 2x. The derivative of minus 5x would actually be special case number 2. So that would just be 5. And remember, square root of 2 is just a number. There's no x anywhere, so it's not a function of x. Therefore, we're just taking the derivative of a constant. So that's actually special case rule number 1. So this just comes out to 14x minus 5. All right, so let's go ahead and look at C. If we're trying to find the derivative of the cube root of x, then this, so you might not see a rule that would apply directly here, but my suggestion is anytime you are maybe dividing or seeing a radical, we can always convert that notation back into exponent notation, and if you can convert it back into exponent notation, then you can apply rule number 1. So we can recognize that the cube root of x is the same as x to the 1/3 power. So we want to find the derivative of that. So then we just apply the power rule. So this is 1/3 times x to the 1/3 minus 1. So our derivative here is actually 1/3 x to the minus 2/3. So basically what we did was we rewrote using algebra, just an exponent rule from arithmetic, and then we applied rule number 1. Okay, so one thing, we can't find derivatives of products and quotients quite yet. The rules do not work as we might imagine they did for adding and subtracting, let's say, but there are rules for them. However, this one is a quotient and we can actually find the derivative, and the reason is we can use some algebra techniques to change the way it looks so we can rewrite everything in terms of the power rule. So I'm not taking any derivatives yet, but I'm just applying the common denominator and splitting apart the top, so I can actually write that as 7x squared over x plus 1 over x. And then I can cancel x, so I can actually just look at taking the derivative of 7x. And again, 1 over x, I'm going to rewrite that using exponent notation. So that's plus x to the negative first power. And then I can just take the derivative of both parts. So 7x is just a line through the center, so that has slope 7. So the derivative of 7x is 7. And then for x to the negative first, we bring down the 1. And we subtract 1 from that power. So negative 1 minus 1 is actually negative 2. So this simplifies to 7 minus x to the negative 2, but you may also write that as 7 minus 1 over x squared. Since they started with fraction notation, maybe we would leave it that way. But anyway, this is the basics, so the introduction to the definition of the derivative, finding derivatives from the ground up using the limit, and then some shortcut rules for your basic polynomial style functions and also power functions. Anyway, this is Dr. Lennon signing off.